Okay, let's unpack this. Today, we're diving deep into something absolutely fundamental in the world of computing.
Mm-hmm.
A concept that, seems simple on the surface, but it's utterly essential. We're talking about the queue.
Exactly. And
Yeah.
we're using some great material from Hello Algo today, which lays it all out really clearly.
Yeah, it provides a really structured look. So our mission really is to cut through any jargon,
Mm-hmm.
get right to the heart of what a queue is, figure out how it actually works, like under the hood,
Mm-hmm.
and crucially, see why it matters to you, the listener, and the systems you use constantly.
Mm-hmm.
We want this deep dive to give you an understanding that, well, actually sticks.
Let's do it. So at its core, a queue is what we call a linear data structure.
Linear, okay.
And the easiest way to think about it, just like Hello Algo suggests, it's simulating the idea of lining up. Waiting for coffee, waiting for ticket.
Ah, the classic line analogy. Yeah, that makes immediate sense.
It perfectly captures the core idea, which is first in, first out. FIFO.
FIFO. Right. So the very first person or element that gets in the line.
Is the very first one that gets out or processed. It's fundamentally the opposite of a stack, right? Which is last and first out.
Yeah, like that stack of plates. You always grab the top one, the last one added.
Mm-hmm.
A queue is much more orderly. No cutting allowed.
Precisely. So thinking about that line, new elements always join where?
At the back. Right. The end of the line.
Exactly. We call that the rear or sometimes the tail. And elements leave from?
The front. The head of the line?
Yep, the head or the front. Simple as that.
Okay, so the actions have specific names too, don't they? Adding to the rear is?
Enqueue.
Enqueue, okay. And taking one off the fronts.
Dequeue. Those are your main actions. Hello Algo also lists the other standard things you'd expect to be able to do.
Like checking who's at the front without removing them.
Right, that's peek. And push is often used for enqueue, pop for dequeue. The names can vary a bit depending on the programming language, as the source notes.
Makes sense. And finding out how many are in the queue.
That'd be size. And of course, checking if it's empty is empty. Pretty standard stuff.
But here's the really cool part, the performance angle. Why are queues so important for, managing busy systems?
Yes. The efficiency. Those key operations, push or on queue, pop or dequeue, and peak, they typically have a time complexity of O1.
O1. Okay, let's translate that. What does O1 really mean for someone listening?
It means constant time. Basically, the operation takes the same amount of time regardless of how many items are already in the queue.
So whether there are, 5 items or 5 million.
Adding one more or taking the next one off is just as fast. It doesn't slow down as the queue grows.
Wow, okay. That is huge for performance. You absolutely need that if you've got tons of requests coming in.
Exactly. You don't want the management system itself becoming the bottleneck, so that O1 speed for adding and removing is, well, it's the queue characteristic.
Okay, so we get the concept FIFO O1 ops. How do we actually build one? How is it implemented in code? Hello Algo points to 2 main strategies.
Right. You need a structure that lets you add easily at one end and remove easily from the other. The 2 common ways are using a linked list or using an array.
Let's start with the linked list. That feels kind of natural for this, doesn't it? Adding and removing at the ends.
It really does. Conceptually, you just say, okay, the node at the very beginning, the head node of the list, that's the front of my queue.
And the node at the very end, the tail node.
That's the rear of the queue. So
Yeah.
the rule is simple. You only add new nodes at the tail end, and you only remove nodes from the head end.
So enqueue means adding a node after the current tail.
Yep, and then updating the tail pointer to that new node.
And dequeue means just taking the head node off.
Essentially, yeah. You grab the data from the head node, and then you update the head pointer to point to the next node in the list, as long as you keep track of both the head and tail pointers.
Both operations are O1. Because you're just fiddling with pointers right at the ends. You're not searching through the list or anything.
Exactly. It maps very nicely.
Okay, that makes a lot of sense. Now, the array version sounds trickier. Because arrays aren't usually great at removing from the beginning.
That's the initial thought, yeah. If you used a basic array and literally removed the element at index 0 for every dequeue, you'd have to shift all the other elements down.
which is slow. That's O-Y-O-N, right? Gets slower the bigger the queue gets.
Totally defeats the purpose. So the array implementation needs a clever trick, which Hello Algo explains, well, you don't actually shift anything.
No shifting. How does that work?
You use pointers, or rather indices. You have an index, let's call it front, that just points to the array slot holding the element currently at the front of the queue.
Okay.
And you also keep track of the size, how many items are actually in the queue right now.
Right. But where do you add new items? Where's the rear index?
Yeah, the rear index isn't stored directly like front. It's calculated. It's simply rear, front plus size.
Front plus size. Okay, so that points to the slot after the current last element.
Exactly. It points to the next available slot where a new element should be enqueued. So the actual elements currently in the queue live in the array slots from index front up to index rear 1.
Got it. So the queue occupies the array slice front, rear 1.
Precisely. That's the effective interval. And now look how the operations become fast.
Okay, walk me through on queue into queue with this index system.
To enqueue a new item, say num, you just put it into the array at that calculated rear index. Num's rear equals num. Then you just increment the size counter, boom, O1.
Nice, just writing to a spot and bumping a counter. And dequeue.
Even simpler, conceptually. To dequeue, you just increment the front index. Front plus plus day, and decrement the size.
That's it. You don't, like, clear out the old value or anything?
Nope, the front pointer has moved past it. As far as the queue logic is concerned, that old element is gone. It's no longer in the front rear 1 range. That's also O1.
That is pretty neat. You're just moving the window, basically, the start and end points within the array. But wait, what happens when front or rear hits the end of the physical array? If you keep adding and removing, what you run out of space at the end, even if there's empty space back at the beginning where you dequeued things from.
Exactly the problem. You'd walk off the end, and that's where the final piece of the puzzle comes in. The circular array.
Circular. So you treat it like it wraps around.
You got it. Think of the array as a ring. When you go off the end, you reappear back at the start. Hello Algo highlights this.
How do you actually do that in code?
With the modulo operator.
Yeah.
When you calculate the next position for front after a dequeue, or rear before an enqueue, you take the result modulo the array's total capacity.
Ah, right. So if the array has length 10, indices 0 to 9, and front is 9, then front plus 1 is 10, but front plus 1% is 0. It wraps back to the beginning.
Exactly. So index plus 1% capacity handles the wraparound automatically for incrementing front, and front plus size % capacity handles calculating the potentially wrapped rear position. It lets you keep reusing the array space indefinitely without shifting.
That is genuinely clever. Okay, so you get O1, add and remove using an array, but with this wraparound logic.
It's a very efficient implementation, but as the source points out, this specific array approach does have one notable limitation.
Which is?
It has a fixed size. You have to decide the maximum capacity of the array when you create it.
Right, unlike the linked list version, which could theoretically grow forever.
Correct. Now, Hello Algo does briefly mention that you could use a dynamic array, one that can resize itself automatically to get around this fixed limit. But it kind of leaves the details of how you'd implement that as, an exercise for the reader, or listener in our case.
Something to think about. Okay, cool. So we've got the FIFO idea, the O1 operations, and these two build methods, linked lists, and these smart circular arrays. Let's connect it back out. Why does this matter so much? Where do we see queues running the show in the real world?
Oh, everywhere, once you start looking. The source gives a great example. Amazon orders. Think about massive sale events like Singles Day or Black Friday.
Millions of people clicking buy at roughly the same time.
Exactly. The system can't possibly process all those orders instantly and simultaneously. So what happens? They go into a queue.
First come, first served.
Yeah.
Or first ordered, first processed, hopefully.
Pretty much. And the system needs to handle that insane level of traffic, that concurrency, without falling over. That O1 efficiency for adding orders to the queue and pulling the next one off to process, it's absolutely critical there.
Makes total sense. You need adding and removing to be lightning fast, no matter how backed up the order queue gets.
Another big area mentioned is just general to-do lists or task processing. Anytime you have things arriving that need to be handled sequentially in the order they arrived.
Like my printer. I send 3 documents. They don't print all at once. They line up in the print queue.
Perfect example. Or maybe calls coming into a call center waiting for the next available agent. Even operating systems use queues internally to schedule which task gets to run on the processor next.
Oh, interesting.
And the source mentions restaurant kitchens managing food orders. Ticket comes in. joins the queue for the cooks, gets prepared in order. It's that same fundamental pattern.
Right. All these different applications share that basic need, process items in the order they showed up. First come, first served.
It really is foundational. Understanding queues helps you see the underlying logic in how so many systems manage flow and handle tasks fairly and efficiently.
Okay, so wrapping this deep dive up, we defined the queue that's strict first in, first out rule. We look at the key operations like enqueue, dequeue, peak, and why their O1 efficiency is so important. We explored how they're built, either with linked lists, which fit naturally, or using those really quite clever circular arrays to get O1 with array storage.
Yep, reusing the space with the modulo trick.
And we saw them in action everywhere, from handling, massive Amazon order surges to just managing your print jobs or a restaurant's order.
And getting a grip on this structure, it's not just theory. It really helps you understand the why behind how lots of systems work, why tasks wait their turn, how order is maintained under load.
Absolutely. So as we finish, here's that final provocative thought for you, the listener, building on what we discussed. We talk about how that circular array implementation is super fast, O1, but has that fixed size limit you set up front.
Right, the capacity is fixed.
So think about this. What kinds of problems could that fixed limit cause in real-world systems where you can't always predict peak load? Where the number of items needing to queue up might suddenly surge way beyond your initial estimate.
Yeah, what happens then?
And remembering that hint from Hello Algo about dynamic arrays, how might you go about designing a queue that could actually grow automatically when needed? How would you combine the queue idea with something that can resize? That's something to maybe mull over, or, if you're feeling ambitious, even try coding up yourself.